Hi, Johnny Hancock here. Welcome to the Keysight Oscilloscope webcast series. Today, we're going to be talking about power supply frequency response measurements using an oscilloscope. Now, you typically use an oscilloscope for a broad range of power supply measurements, but there are a couple important measurements concerning frequency response where you typically have to turn to a frequency response analyzer or a network analyzer, which are specialized instruments. But today we're going to talk about those measurements, and specifically power supply rejection ratio, as well as control loop response, in other words, Bode, gain, and phase, and show you how they can be performed with an oscilloscope with a built-in source or waveform generator, and a special option that enables it to do all of this automatically. So you're welcome to watch the entire webcast, or you can click on the time tags below and just jump to any subtitle, any section you're specifically interested in. So let's go to the agenda now.
We're going to start with output ripple, and the reason, as I mentioned earlier, is so we can see, looking at the output in the time domain, to understand some of the issues. And one of the most important issues is how you probe the output. We're going to be looking at very low-level signals, and the way you probe it is probably the most important thing. And then we'll also take a look at how you can do some analysis looking at output ripple using FFT. Next, we'll move into power supply rejection ratio, talk about what it is, and then take a look at measurement results using a scope with a built-in generator, and then also using a network analyzer. And then we'll move into control loop response, or Bode, gain, and phase plots. We'll first address transient response, which is very much associated with a control loop response. How fast does the response respond to a change? And we'll look at the results on a scope as well as a network analyzer. Then we'll wrap it up. So some of the design trends today with power supplies, people want to improve efficiency, increase power density, increase reliability, control EMI. What you can see there highlighted in red, improve output power rail integrity. When we talk about power rail, we just simply mean the DC output, improving the purity of your DC output. If you have lots of noise and ripple and disturbances, slow responses on the DC output, that can directly affect the circuitry you're trying to drive. If you have high-speed digital circuitry, if your power rail is moving up and down, then your threshold levels are moving up and down. If they're moving up and down, that induces jitter, and it forces you to run your systems at a slower than optimum speed. And then some of the other issues here, decreased thermals, reduced cost, that all adds up to increased test time. So let's first talk about output ripple. What is it? You can see a diagram I've drawn there. Sometimes people just call it output noise. Another term that's really getting popular today is power rail integrity, and another term is PARD, periodic and random deviations. It's typically in the tens of millivolt range or lower, so sometimes it can be very difficult to measure accurately with a scope. The type of probe you use and the way you connect is extremely critical as to how accurate you're going to make output ripple measurements, as well as power supply rejection ratio and control loop response measurements. But sometimes these issues, how you connect, how you probe, are often overlooked. And the scope baseline noise floor and the minimum input sensitivity, meaning how low can you make volts per division, can also limit your ability to make an accurate output ripple measurement. So these are the two most popular type of probes that are used to measure output ripple. The one on the left, that's what comes with your scope, a 10-to-1 passive probe. And unfortunately, that's what most people use to measure output ripple. It's got some good points I've highlighted in green there. Comes with your scope. You don't have to pay more for it. Has relatively acceptable high bandwidth, especially for output ripple measurements, up to about 700 megahertz bandwidth. It also magnifies the DC offset range by a factor of 10. So if your scope has at its minimum input sensitivity only has 2 volts of DC offset, or perhaps 5 volts of DC offset, and if you want to measure, say, a 12-volt supply, using a 10-to-1 probe, you can easily do that without using AC coupling. And we'll talk about later why that is sometimes important. Some of the drawbacks of a 10-to-1 passive probe is it does limit your vertical input sensitivity by a factor of 10. So if the scope has a minimum input sensitivity of 1 millivolt per division, as soon as you connect a 10-to-1 probe to it, now it's 10 millivolts per division. And it also magnifies the scope noise floor by a factor of 10. Typically for output ripple measurements, a 1-to-1 probe is a better option because it optimizes your vertical sensitivity. It minimizes the scope's noise floor, but it does have a few drawbacks. A 1-to-1 passive probe, about the maximum bandwidth you can get out of it is about 35 megahertz. Sometimes this is not an issue. A lot of people only make power supply measurements and they use bandwidth limit on the scope, which limits it to 20 megahertz anyway. Another drawback is it limits your DC offset. So if you want to measure a 12-volt supply at 5 millivolts per division, you simply can't do it. You have to use AC coupling. And you have to pay extra for it, but 1-to-1 passive probes are relatively inexpensive. So let's now talk about the ground lead that comes with both of these probes. What is a ground lead? If you're measuring relatively high-level signals that are also have a high-frequency content to them, it's actually a big inductor, and it can really reduce the bandwidth and the response of your signals. But for the measurement we're talking about, you're measuring very low-level signals, relatively low frequency. It acts as a giant antenna. So let's take a look at different probing techniques. So there you see on the left, this is unfortunately what I believe most people are doing. They're just using that standard ground lead. And you see that big loop there. That will pick up all sorts of trash that's in the air. A better grounding technique, typically probes, whether they're from Keysight or other vendors, they have various adapters inside the little bag that the probes come in. This is a little spring clip, gives you a very short ground connection, and you can get a pretty good ground connection. It's a relatively small antenna. Now, it's not going to pick up too much environmental noise. A better connection, if you're lucky, you might have your probe point as well as some grounding point or post nearby, as I'm showing here. This gives you a very good connection, and the absolute best connection you can see there is to install a probe socket on your board. The barrel of the probe, if you pull the cap or the end of the probe off, the grabber part, the barrel of the probe is ground. So that's what you see in the better one with the post, with the barrel leaning up against the post. If you install it inside the socket, that gives you the absolute best grounding and the smallest antenna effect. So let's take a look at some actual output ripple measurements using various probing techniques. We're going to start with the worst probing technique. What I'm measuring here is the output ripple on a 3.3 volt linear regulator. I'm using a 10-to-1 passive probe, and I'm using a standard ground lead like you can see in the picture in the lower left. And in the left side of the screen here, you can see I've expanded the output ripple measurement, which is basically just a volts peak to peak, and it's measuring 167 millivolts peak to peak. Now, notice the words I have there at the bottom, SMPS in the neighborhood. There's a switch mode power supply on my bench. I'm not measuring that power supply. It just happens to be on the bench, and it's radiating all sorts of energy. If I turn that switch mode power supply off, you can see we reduced nearly in half from 167 millivolts down to 94 millivolts peak to peak. And then, if I take that ground lead off and plug it into my probe socket, now we've gone down by a factor of 3 again. Now we're down to 34 millivolts. Things are looking pretty good, but the output ripple on this linear supply is actually a lot lower than 34 millivolts. The problem I have now is I'm using a 10-to-1 probe, which limits my input sensitivity to the minimum 10 millivolts per division. Right now I'm set at 30 millivolts per division. This next slide, I've used a 1-to-1 probe. Now you may say, well, it looks like the same thickness of a trace, but I've changed from 30 millivolts per division down to 3 millivolts per division. Now I'm measuring 3.4 millivolts peak to peak output ripple. And then if I turn on the bandwidth limit, which a lot of people recommend doing, I'm down to about 1 millivolt peak to peak. So as you can see, we started at 167 millivolts with poor probing, and now we've gotten down to actually less than 1 millivolt of energy that's under 20 megahertz on the output of this linear regulator. So big difference, and the only difference, I'm measuring the same device, the same output. The only difference is I'm using different probing techniques. Now let's take a look at a switch mode power supply as opposed to a linear power supply. So this is a switch mode power supply with a 5 volt output with a switching rate of 2 megahertz. You can see the yellow waveform in the bottom there. That is the DC output. And I'm using DC coupling, and you can see I've got my DVM turned on. It's measuring 4.98 volts, and the output ripple is 23.1 millivolts. Now, right away I'm using the best probing techniques. I'm using a 1-to-1 probe, and you can see in that picture in the lower right, I'm leaning the ground of the probe, the barrel of the probe, up against a ground post, so I get a very good ground technique. So you can see some fuzz writing on that 2 megahertz waveform. The purple trace up above is I'm running a FFT, fast Fourier transform, on this waveform to see what kind of frequency content is in there. Now you can see the largest bump in the FFT in the upper left is the fundamental, and that's right up there at 2 megahertz. And then you can see several other peaks that are looks like they're probably harmonics of this. However, you take a look at that second highest bump, which is right around the third harmonic. Sometimes it looks like 2 lobes, and sometimes they merge into 1. The problem I have here is I don't have good enough frequency resolution on my FFT measurement. I can improve my frequency resolution simply by rescaling my time base. So right now I'm looking at about 3 cycles across screen. Here I've changed the time base to put 200 cycles across screen and using the scope's deep memory. And now I have very good frequency resolution. I can clearly see the fundamentals and all the harmonics, but I can also see what I might call an oddball frequency. It's right up there, right close to the third harmonic, which is right around 6 megahertz. There's another one sitting there at 6.78 megahertz. So that's what the FFT can do for me. It can draw out other components of interference that may be increasing my output ripple, and then I can begin hammering down various components to try to improve my output ripple. Now this 6.78 megahertz, it just happens to be the same frequency as a wireless resonator. If I turn that resonator off, bang, it goes away. So there's one source of my output ripple. It did reduce the overall output ripple by a couple of millivolts. So let's go back to the 10-to-1 versus the 1-to-1 passive probing issues. Remember the limitations I mentioned of the 1-to-1 passive probe. And by the way, the 1-to-1 passive probe, for the measurements I just previously did, was the right probe to use between these two, because the 10-to-1 passive probe reduced my input sensitivity such that I couldn't measure this low-level noise. With the 1-to-1 passive probe, I can clearly see the output ripple, but I still have two relatively big limitations. One is bandwidth, and the other is the DC offset capability. Now let's talk about what is the solution to that. This is a new probe that Keysight introduced about 6 months ago. It's the N7020A power rail probe. It's an active probe, and it's a 1-to-1 probe. It's got 2 gigahertz bandwidth, and it also has up to plus and minus 24 volts of offset. It is not a general purpose active probe that you would typically use on high-speed digital signals. It was specifically designed for measuring output power rails, the DC signal, and with the DC offset of plus or minus 24 volts, we can preserve that DC component. And I'll show in a few minutes why that's important. So let's take a look at the same measurements we did earlier. This is on the switch mode power supply with a 2 megahertz switching rate. And now I'm using the 1-to-1 active power rail probe. And what you can see the arrow pointing to there is high frequency stuff that was hidden before because of the limitation of the 35 megahertz probe. Now we can see this other high frequency information, and the overall output ripple has increased about I think about 50%, went up from about 20 millivolts peak to peak to over 30 millivolts peak to peak, because now we're seeing things the other probe was hiding. And if I change the time base so I can do a better FFT, we can see all these higher frequency harmonics that, again, the standard 1-to-1 passive probe was hiding. Now, why is DC offset range important? Here's an example. So here I'm showing a power supply that's 8-volt DC supply, and at this point I'm probing it with a 1-to-1 passive probe, not the active probe, not the power rail probe. And since it's 8-volt DC supply, I have the scope set at 5 millivolts per division. I am forced to use AC coupling to get rid of the DC component. And so now I'm measuring approximately 5 millivolts of peak-to-peak output ripple. Now I've got the time base of the scope set up on a pretty slow time base range, 500 milliseconds per division. And so we got 5 seconds across screen. If your screen is large enough, perhaps you can see looks like some very low frequency modulation going on that output DC supply. My next slide, now I've changed over and I'm using the 1-to-1 active power rail probe, which has plus or minus 24 volts of DC offset. So now I can preserve the DC component, and now all of a sudden you see this very slow modulation has gotten much larger, and now I'm measuring 15.2 millivolts. The problem with AC coupling is not only does it get rid of the DC component, which the average DC component is not that big a deal. If you want to know what your DC supply measures, you can just stick a DVM on it and measure what is my DC supply, and you're going to get a more accurate measurement than the scope. But the problem with AC coupling is not only does it get rid of that DC component, the average DC level, it gets rid of low frequency AC or low frequency drift. The typical cutoff frequency on AC coupling is about 10 hertz. So anything below 10 hertz, it kills. And in this case, I've got about a 500 millihertz modulation going on this particular supply, and the 1-to-1 active probe with a large DC offset preserves that. So here's our next polling question, and again, I'm going to share the results. Pretty simple question. How much output ripple is tolerable in your power supply designs? Up to 5 millivolts peak to peak, up to 10 millivolts, up to 20, or up to 50. So go ahead and select one, select submit, and let's take a look at the results. Most people, it's under 10 millivolts peak to peak, but it's pretty widely spread out there. So I think some of the issues I talked about here today, the way you probe it, if you're trying to measure things under 10 millivolts peak to peak, the most important issue that you need to pay attention to is how you probe it, how you ground it, and what type of probe you use. And these also apply to what I'm moving into next, and that's power supply rejection ratio and control loop response. So let's move into what you probably thought this whole webcast was about, frequency response measurements. So power supply rejection ratio, sometimes a lot of people just say PSRR. Some people call it power supply ripple rejection. What it does is it measures how well the device, such as a DC to DC converter, voltage regulator, LDO, or so on, how well does it reject various frequency components injected at the DC input. And so, to put it bluntly, it's basically a garbage in, garbage out measurement. You put garbage on the input, how much sneaks through? And the calculation for it is simply 20 log V in over V out. Now, a lot of people argue Well, no, shouldn't it be 20 log V out over V in, which is the gain for a Bode plot? That would be for plotting and measuring gain. This is plotting and measuring rejection, which is just the inverse. Now, you can do it the other way around and you'll get an inverted plot. Or, using whatever instrumentation you're using, you can flip-flop your V in and V out to get the plot you need. So it's pretty simple. So here we show a diagram of doing a PSRR measurement on LDO. You simply connect your probes to V out, V in, and then you have to modulate the DC input with a source. Now, it could be an external generator, it could be a source from a network analyzer or a frequency response analyzer, or in the case what I'm going to show, it's a function generator that's built into the scope. But you can't directly connect that generator directly to the DC source. They will short each other out. You need to go through some sort of summing device. Now, some people say, well, you can use capacitors and inductors on different legs of this, but that limits your frequency range. There are summing devices, and what I'm going to use is what I'm showing here, is a line injector from Picotest called the J2120 line injector. So here's the physical test setup that I'm using. There you can see my Infinivision 4000 X series oscilloscope. The BNC on the far left is the function generator channel 1. It has two generators on it. I'm using the channel 1 output going into one input of the line injector. I have my DC input in the lower left going into the other input. The output, right about in the middle of your picture, is the modulated DC. That's powering up my evaluation board. This is a linear supply from Picotest. And then you see my two oscilloscope probes. Now you notice the input one, the one on the left, I'm using a 10-to-1 probe, and I'm using my big antenna, my ground lead. And I can do that because I'm modulating this signal with a couple hundred millivolts. So I'm not down there in the millivolt range trying to pull things out of the scope's noise floor. I can use a 10-to-1 probe, and the ground lead doesn't seem to have much effect at this level. However, on the output side, I'm using a 1-to-1 probe that's going into channel 2 of the scope, and I'm also using my probe socket so I don't have that antenna effect, because the output levels are going to be extremely low. So let's take a look how you set it up on the scope. You go into the Power app, which is an option on the scope. There's the pop-up list showing the various power measurements. Select the PSRR measurement. And then you go into what's called the Signals menu, and there's a pop-up screen that shows you a diagram, gives you some tips on where to connect your probes, how to modulate your DC input, and then you can also assign, okay, which of the scope's channels. If it's a 4-channel scope, you can use any of the 4 channels, which is V in, which is V out. And then there's a signals or setup menu where you can define your test parameters. So start frequency, stop frequency, max plot ratio, and the amplitude of your disturbance signal. In this case, I don't know if you can read it or not, I have a start frequency of 100 hertz, stop frequency of 20 megahertz, which is the maximum. I'm going to max plot ratio up around 70 dB, and I'm going to modulate it with 350 millivolts peak to peak. Now, if you're doing this with a standalone scope and a standalone generator, if you do it manually on your bench, it's going to be very tedious. You can set the generator to frequency, note the voltage reading on V in and V out. You could either measure peak to peak, or you could measure RMS, take your ratio, move to the next frequency. A better idea would be to program both the generator and the scope. You could use LabVIEW. You could use MATLAB. That might help you plot it. We can do it all in the scope with the power option. So let's take a look at the measurement itself right now. So you press the apply button and it begins the sweep. Now notice the circle up there, the red circle. It's circling 1 millivolt per division. The green waveform is the output waveform. It is sub 100 millivolt peak to peak. It is a tiny, tiny signal. The scope is using averaging to try to pull this out of the scope's noise floor. The purple waveform is the plot of the power supply rejection ratio. I've tried to simulate it here to let you know how fast it runs. It takes about a minute to do one sweep. It doesn't repeat. It only does it one time. When it completes it, as you see here, it then pops up the cursors. Then you can slide the cursors along the power supply rejection ratio plot and measure various areas. You can see the maximum rejection we were measuring is up there in excess of 70 dB. I've heard a lot of people say, no, the best you can get out of an oscilloscope is about 50 dB. Well, with the techniques that we've used here, we can get up to in excess of 70 dB, as you see here. Now, I saw, before I put those probe sockets on my board, prior to that, I was using the spring clip. I got about a 4 dB improvement simply by going from the spring clip to the socket. So, little things can make a big difference. Now, how does this compare to the typical type of instrument that you would use for this measurement, which would be a network analyzer, or some people just call it a VNA? The VNA is certainly better. You can see, but they do track very closely. The VNA has much higher dynamic range. The maximum rejection in this case, the VNA measured, was close to, it's about 79.6, close to 80 dB. The scope, the maximum point I picked off there was about 74 dB. However, I'm not going to claim that 74 dB was accurate, but it was up in the noise area of the scope. Once the plot got down to around 65 dB and lower, it tracked very, very closely to the measurement on the network analyzer. So let's move into control loop response. But as I mentioned early on, closely related to control loop response measurements is transient response. And if you're wondering what a transient response measurement is, here we show one on the scope. If the green waveform you see there is the output current of a DC supply, the yellow waveform is the output voltage of a DC supply. If there is a sudden change in the load, in this case you can see a step from a low current to a high current, there would be a sudden change in the output voltage as well. So if you have a sudden increase in current, increase in load, there will be a sudden decrease in voltage, and then there's a feedback network in the power supply that will try to correct for that. And there you can see the correct, and you can see some ringing, and then it settles out. There is a closed loop negative feedback amplifier in your power supplies that are controlling this response, the response time, the amplitude of the response, and this can be tuned to be optimum. Now, in this slide we show a simplified block diagram of a DC to DC converter. That negative feedback control loop is basically made up of, if we look at DC only, R1 and R2, there's a resistor divider network, and then that voltage is compared against a reference voltage that feeds into an error amplifier. Then the output of the error amplifier then controls, in this case, if it's a switching supply, it's going to control perhaps a pulse width modulator. So if you have a sudden dip in output voltage, there will be the error amplifier will detect that with negative feedback and try to give an increase in the duty cycle of the pulse width modulator, so the on time or the conduction cycle of the switching transistor is on more often than it was before, to try to pull that voltage back up. Now, that's the DC look at it. Now there's also a compensation network that you can tune for how fast you want that response, and that's made up of C1, C2, C3, R1, 2, 3, and 4. Now you can tune those various components to get the type of response you want. Now let's take a look at the typical loop gain measurement that you might want to do using a network analyzer, or as in the case I'll show in a few minutes, the oscilloscope. The gain plot, you'll typically start off with a gain up there maybe around 40 or 50 dB, and then it will slow down. And then there's a phase plot. The two most important points you're looking for, probably the most important one, is the phase margin. The phase margin is always measured at the 0 dB crossover. So where V in and V out, and I'll show you where those are measured in just a few minutes, where those are equal, you want positive phase margin. If that phase margin ever becomes 0 or negative, you no longer have negative feedback. You have positive feedback. And when that happens, you're going to have an output that oscillates. It's going to be an unstable output. The other point that is sometimes important to measure is gain margin. And that's where the phase crosses minus 180 degrees, or the phase margin is 0. And there's the phase margin. So the higher the 0 dB crossover frequency, the faster the response will be to load changes. The higher the phase margin, typically people try to design for something greater than 45 degrees. The higher the phase margin, the more stable your output power supply is going to be. Lower gain at higher frequencies, you have better noise immunity, lower output ripple. And so these are things that you as a power supply designer must optimize for what your design criteria is. And the last point I got there on the bullet, here you see the plot plotting the phase. Most network analyzers, not all, will plot the phase margin. So they go ahead and plot the difference for a closed loop measurement. So let's take a look at another schematic of how we're going to make the measurement using the scope. To make this measurement, typically you have to insert what we call an injection resistor. It's a very low value resistor you insert in series with that R1, R2 resistive divider network that's going into that error amplifier. R1 and R2 are typically in the tens or hundreds of K ohms. In this case, there's a 5 ohm resistor in series. I've seen various application notes from various sources. They recommend anywhere from about 10 ohms to 50 ohms. The device I'm going to test in a few minutes is very sensitive, and we just have a 5 ohm rejection resistor in it. Now, across that 5 ohm rejection resistor, you want to generate a differential voltage, very low level voltage, in order to force current to flow through that resistor and modulate that feedback network. You can't directly connect the network analyzer, or unless it's isolated, or you can't connect a function generator directly across those resistors. If you do, you'll ground one of those points. It must be floating. Therefore, you have to use another accessory, in this case an injection transformer or an isolation transformer. In the test I'll show in a few minutes, I'm going to use a PicoTest 2101 injection transformer. So here you can see the output of the function generator connected to the input of the transformer. V out, the DC output, I've got connected to channel 2. You could connect it to channel 1 if you wanted. And V in, which is the high side of the resistor divider network, I've got connected to channel 1. And this is just a conventional Bode plot. It's going to plot gain as 20 log V out over V in, or in this case, V from channel 2 divided by V from channel 1. Now, I'm showing the scope with the built-in generator. Again, you could do this with a standalone scope and a standalone generator. This is my physical test setup. Looks somewhat similar to the one I had before. There you can see the output of the generator in the upper left goes to the input of the isolation transformer. The output of the isolation transformer goes to 2 test points that are across that injection resistor. My DC input down in the bottom middle of that diagram. And now the 2 scope probes I'm using, they're both 1-to-1 probes, and I'm using probe sockets on both of them. The output levels on both input and output this time, both of them, are going to be extremely low-level signals. So I've got to use 1-to-1 probes. Here's how we set it up on the scope. Again, select the power option, pop up the various measurements, and then select Control Loop Response. In the Signals menu, again, a different diagram will pop up, give you some hints on how to make your connections, and again, you can assign whose input, whose output. In this case, I assigned input channel 1, output channel 2. And then in the Settings menu, this is where I can define, again, my start frequency, stop frequency, my minimum plot ratio, my maximum plot ratio, and the output amplitude. Now, I don't know if you can read it or not. The amplitude there says 130 millivolts peak to peak. At this setting, the scope's generator thinks it's driving a high impedance output, but it's not. That isolation transformer has about an effective 5 ohm input impedance. And so the actual voltage that's going to be across the input of that one-to-one transformer is only going to be about 12 millivolts peak to peak. So we're driving it with a very low-level signal. Again, if you don't have this, our scopes, the InfiniVision X Series, don't have this option built into it. If you're using an external scope, external generator, you can do this with LabVIEW and MATLAB. So here's the measurement. You press apply. It works similarly to the power supply rejection ratio. You'll begin to see the gain plot creep across there. If you look up top there, you'll see channel 1 is 1 millivolt per division, and it started out well below 1 millivolt. At this point, we just crossed our 0 dB crossover, and it's going to continue to creep across. Now, it's kind of jumping across, but when you're really doing the measurement, it's creeping much smaller steps than what I'm simulating here. Again, when it completes the measurements, the cursors pop up, and then you can position them, and this is where you would measure the 0 dB crossover. You'd slide the X1 cursor over until slide the X1 cursor over until the Y1 cursor measured as close to 0 dB as possible. In this case, it's measuring minus 113 milli-dB. That's the 0 dB crossover at 6.85 kilohertz. Now, the next thing you might want to know, okay, where's my phase plot? On the bottom of the screen, you can see, I think I'm going to actually show a hand pop up where it says Plot View Gain. If you press that button, it will toggle to plot phase. It doesn't do another measurement. It did the phase measurement while it was doing the gain, but it can only plot one at a time. And so here's the phase plot. And from here we can see at that frequency, 6.85 megahertz, the phase margin was measuring about 65 degrees. Now you may say, wait a minute, where's the rest of my phase plot? I'm only getting a short segment there. That's one of the limitations of this measurement on the scope versus a network analyzer. The scope can't measure phase in the time domain if the signal level is below 1 millivolt peak to peak. And that's using a 1-to-1 probe. That's 1 division peak to peak. If the signal is below that level, we can't measure the phase. Now, the circuit I was measuring was a very sensitive circuit. Other circuits, you could input a higher disturbance signal. You could probably get a more complete phase plot. Another way to measure the phase is you could actually set up the phase measurement itself. So after completing a phase measurement, you determine the 0 dB crossover point. Just go back into the time domain and you can directly measure phase. So here we're measuring 65 degrees. I could change my generator to any frequency I want, change the time base, and continue making phase measurements. So I could probably push it a little bit further doing manually to get the phase measurements plus or minus what it was showing before. But it becomes difficult to measure the phase, especially because of the signal and noise ratio, if the signal is below 1 millivolt peak to peak. So how does this compare to the network analyzer? Well, the gain plot tracks pretty darn closely. We measured on the scope 0 dB crossover at 6.85. The network analyzer, this is the Keysight network analyzer, measured 7.11 kilohertz. Phase margin, scope measured 65 degrees. The network analyzer measured 68 degrees. Clearly, you can see one of the advantages of the network analyzer is it's going to plot both of them simultaneously. On the scope, you have to select one or the other, and then you just get a partial plot of the phase on the scope. But if it's just the phase margin that's most important, you can do that. Now, we couldn't, in this particular instance, measure the gain margin. So let's kind of review, summarize scope versus network analyzer. The scope can make these loop gain measurements up to 20 megahertz. That's the limitation of the function generator. One of the advantages is you can view the time domain waveforms during the test. That can sometimes be important. If you're overdriving, if the disturbance signal has too high of amplitude, you can induce distortions on your waveforms. Your waveforms won't be sine waves anymore. If you're using a network analyzer or a frequency response analyzer, you won't know that. With the scope, you see each waveform that's being tested at each frequency, and you can visually look and see if you're getting distortion. With the scope, the measurements are often good enough. They're not as good as a network analyzer. It does have limited dynamic range, but for linear supplies, I've shown that the results are very good. On switch mode power supplies, not so good. It depends on the signal-to-noise ratio. If there's a lot of switching noise on the output of supply, and you're trying to measure a control loop response or power supply rejection ratio with the scope, the results have limitations.
Here's an update on what I just presented since we originally broadcast this webcast. Since then, we have made significant improvements using an entirely different measurement algorithm for our frequency response measurements. So there is a significant improvement in dynamic range. You can now use this on both linear and switch mode power supplies, even if there is significant output switching noise. There's also an entirely new user interface with a single dialog box, makes setting up these measurements really easy. We also added custom amplitude profiling, so you can customize the test amplitudes at different frequency ranges to avoid distortion and to get the highest dynamic range. We can also now plot both gain and phase on the same display as you see here on this slide, along with an automatic measurement of phase margin and gain margin. And if you take a look at the phase margin plot, which is in orange here, now you can see a full plot of the phase, not just a portion in the middle part of the frequency band like I showed earlier. So things have changed, a lot better performance now, even more comparable to a network analyzer.
Probably the biggest benefit of this measurement capability on the scope is you can use the scope for a broad range of other measurements, other power supply related measurements, switching loss, power quality, transient response, as well as any other general purpose troubleshooting. Plus it can do these frequency response measurements. Now the network analyzer, this particular model can make measurements up to 30 megahertz. It has much higher dynamic range. You can view gain and phase simultaneously. You can also dynamically program the amplitude, so you can start with a bigger amplitude, then reduce it. You got frequency response calibration, plus you can do S parameters and impedance measurements up to 3 gigahertz. So here's my last polling question before we begin to wrap up, and this is for my benefit. Do you currently need to characterize power supply rejection ratio and or control loop response on mostly linear or mostly switch mode power supplies? So the 4 answers: mostly linear supplies, mostly switch mode power supplies, both about equally, or neither. You don't do these measurements. So go ahead and quickly select an answer. And mostly switch mode power supplies. That tells us we need to do a little bit of work, see if we can improve this. I think we can. So thanks for that information. So let's begin to wrap it up here. What have we learned today? Power supply design optimization requires a lot of testing and characterization. The quality of your output power rails often determines how fast your high-speed digital circuitry can run. So if you got a power rail that's bouncing up and down, your signal timing is going to be bouncing back and forth. Choosing the right probe and grounding techniques can make a big difference in the measurement results. The power supply frequency response testing can help you design cleaner and more stable outputs. And Keysight's InfiniVision X-Series scope with the frequency response testing capability is often good enough and certainly a lot less expensive than a network analyzer. So I want to give you an overview of what Agilent, I still say that these days, Keysight offers in oscilloscopes. We've got a broad range of scopes starting from handheld scopes all the way up to 33 gigahertz or 63 gigahertz real-time scopes. The scopes we used today and all the measurements were the 3000T and the 4000 X-Series oscilloscopes. To give you a closer look at that particular family, we call the InfiniVision X-Series. There's 4 different frames, the 2000, 3000, 4000, 6000. Basically, the big differences are the bandwidth ranges, sample rates, as well as prices. The 2000 X-Series does not have the power option. The others do. To give you an idea of what kind of price range you're talking about and how does that compare to a network analyzer or a frequency response analyzer, all of the measurements could have been done with a 2-channel, 100 megahertz, 3000 X-Series oscilloscope, which is priced in the U.S. a little over $3,000. The power option on that is about $1,400. So you add those two together, throw in a couple of $200 one-to-one probes, you're slightly over $5,000 to do all the measurements I showed today. Now the power option is an option. A lot of people claim we nickel and dime them with all these options. There's a lot of options on the scopes. Mask limit testing, waveform generator, various serial bus trigger and decode. We have a bundle of options. You can get them all for one price at a very large saving. Some of the recommended probes. Here I'm showing some of the a pretty broad list of probes for power supply testing. Several of our current probes, as well as high voltage probes. The probes we used today in my testing were just these 3 up here. A 10-to-1 passive probe, which ships with the scope, the 1-to-1 passive probe, and then I probably should have highlighted it more, the new active power rail probe, the N7020A. Keysight also has other products for doing characterization of power supplies, not just scopes. I focus pretty much on the InfiniVision X-Series scopes. We also have the Infinium S-Series. That's a Windows-based scope. This one is actually the best scope if you're trying to measure really low-level output ripple, sub-millivolt or very low millivolts. It's got a very low noise front end, 10-bit resolution. We also have a new IntegraVision AC power analyzer. You see over there in the upper right. We just introduced this product. It looks, feels, and runs a lot like a scope, but it is not a scope. It is a power analyzer. It's primarily for analyzing inputs and outputs. It has isolated inputs, but it does not have the bandwidth of an oscilloscope. It's primarily for lower bandwidth measurements. We also have power device analyzers. You can see the network analyzer there in the middle. I showed some comparison to that. And at the very bottom is a DC power analyzer. Now the DC power analyzer doesn't analyze your DC power supply. It replaces your DC power supply. It is a programmable DC power supply. So you can insert that in place of your power supply to test your DUT under various conditions. So you can have your power ramp up, ramp down, and it also has a scope-like user interface on it so you can see the voltage waveform and the current waveforms. We have a lot of technical resources. I've listed some of the ones that are most applicable to today's webcast, a couple of the app notes. There's one on control loop response, switch mode power and power supply rejection ratio, and we have several videos as well. Now you can download and view all of these. We have a website set up specifically for power measurements using a scope. It's keysight.com/find/scopes-power. You can go there to download app notes, videos, view recorded webcasts. Another resource I'd like to recommend is an expert in the field of power integrity. His name is Steve Sandler. He's the founder and managing director of PicoTest. And as you saw in today's webcast, I used a couple of PicoTest evaluation boards as well as some of their accessories. He's also written a new book called Power Integrity. It's a very good book, so if you're interested, you can get that on Amazon, or if you're interested in interfacing with Mr. Sandler, you can just go to picotest.com. And there's a lot of other good resources out there on the Internet. Just Google frequency response analysis, and you'll find all sorts of stuff. Now, at this point, I want to turn it back over to Bill.
Okay, great. And we will now go and take a look at some of the questions. Johnny, what about using an SMA cable directly to the scope?
You could do that. And the one-to-one probe is almost effectively that. It depends on what you're going to terminate into. If you terminate into 50 ohms, then you've got to figure out whether or not 50 ohms is going to load your signal that much. Or you could terminate into 1 megohm, but if you terminate into 1 megohm, then you limit the bandwidth. So SMA into 50 ohms, and if you can install an SMA connector down on your board, that would give you very good results. Now, one of the connections, I mentioned the N7020A power rail probe. One of the cables that comes with it is an SMA cable. And what a lot of folks are doing with that is they're scattering SMA connectors all over their power distribution boards and measuring the output ripple at various different power points, and then feeding that into the active probe, which has 50 k ohm input. Now, if you can stand 50 ohm input, you can go straight into the scope's 50 ohm input, and that would give you very good results, I think.
Okay. Where can we get probe sockets and design info for those?
Well, from Keysight, if you go to our site, go to Scopes, and I think you go to Oscilloscopes, and if you scroll down, you'll see probes and accessories, and you can eventually get to some of these accessories such as probe sockets. And now those probe sockets are designed specifically for some of Keysight's probes. They may be compatible. If they are mechanically compatible with other vendors' probes, they might be. I'm not sure if they're compatible with Tektronix probes, but if you got a Tektronix scope, I bet you could go to Tektronix site and find similar probe sockets. Now, we have different type of probe sockets. The ones I showed on the boards here were very good quality ones. They're a little expensive. We also have less expensive ones as well.
Okay. In general, for power supply type measurements, is it better to use an active probe, non-powered, versus a passive probe?
That depends. If you need high sensitivity, you're measuring millivolt kind of stuff, you have to use a one-to-one probe. And if you use a passive one-to-one probe, it's got low bandwidth. An active one-to-one probe has high bandwidth. So it depends on if you need the higher bandwidth. Now,
okay.
I think I saw another related question, probe capacitance. The passive probe is certainly going to have more capacitance than the active probe. However, typically when you're probing the output of a power supply, it's got a lot of capacitance on it anyway. So that's not going to really affect your measurements that much.
Okay. How are you determining what amplitude to set the scope to for this measurement? Do you keep increasing it until it's valid?
I think that's probably the best way to do it. I got these evaluation boards from PicoTest, and I asked Mr. Sandler what was the best amplitude to test these at. And then I did various tests at different amplitudes, and I observed the waveforms on screen to see when I started seeing distortion. The higher I can set the amplitude, the higher the dynamic range I can make. The more it pulls the signal out of the scope's noise floor. And so And that's one advantage of the network analyzer, is that you can do this dynamic amplitude setting. So you can start at a higher amplitude where perhaps distortion is not occurring. And then as you move up in frequency, you ramp down to a lower amplitude. The scope can't do that. At least it can't do that today. So it is a little bit of a guessing thing as to what amplitude you can set as to when distortion will occur, and you can just do it trial and error with the scope. I would start low and begin increasing.
Okay. How much oscilloscope bandwidth is required for the measurements?
Well, all the measurements I showed today, we were only doing the frequency response test up to 20 megahertz, and often they're done much lower than that. A 100 megahertz scope would have been more than enough for all of these tests. Okay. Now, that's for these tests. Now, typically when you get a scope, you don't buy a scope specifically for one test, such as the frequency response. You buy it for other things. So, for frequency response analysis, bandwidth's not an issue. You want to evaluate what your other measurement needs are. Maybe some of the, if you're trying to measure switching loss, you may need higher bandwidth. Or if you're doing some higher speed digital circuitry, you may need higher bandwidth. Okay.
What would you do if the ground lead can't be shortened or eliminated?
That's a tough question. If it can't be shortened or eliminated, well, you can try it with a long ground lead, but I think you're going to find out that if you're measuring low-level signals, your signal-to-noise ratio is simply going to be too low. So you can try it, but you may not get good results.
Okay.
You might try no ground lead at all, but if things are floating, that may not work too well.
Okay. Can the scope's control loop response measurement be used to perform other Bode plot gain and phase measurements, such as characterizing amplifiers and filters?
Oh, absolutely. In fact, I think the measurement results would probably be a lot better because you wouldn't be in an environment with lots of switching noise. If you're just measuring a passive filter or an active amplifier, this particular tool is going to work very well. Still probably not as good as a standalone network analyzer, but it's going to do very good.
Okay, well, here's a good one to wrap up on. Are the PSRR and control loop response measurements options on Keysight scopes?
Well, they're part of the power option, so they're included with the power measurements option. You can't get one or the other. You get both, but you also get it along with switching loss, power quality, current harmonics, efficiency, all the others. So it comes as a single bundle. And I think I should, the price of the power option, I think is around $1,500. But today you can get the power option and every other option we got on the scope for the same price, about $1,500. Now, another thing I might mention, another option on the scope is the WaveGen generator. It's a 2-channel on the 4000 series. It's a 1-channel on the 3000 series. You don't need to purchase that option to run these measurements. These measurements will turn those options on for these measurements only.
Okay. Well, that concludes today's presentation.